In the first of the units on algebraic fractions, we looked at what happened when we had a proper fraction with linear factors in the denominator, a proper fraction with repeated linear factors in the denominator, and what happened when we had improper fractions. What I want to do in this video is look at what happens when we get an irreducible quadratic factor. When we get an irreducible quadratic factor, we'll end up with an integral of something which looks like this: ax plus b over ax squared plus bx plus c, where the a and the b are known constants, and this quadratic in the denominator cannot be factorised. Now, there's various things that could happen. It's possible that a could turn out to be 0. Now, if a turns out to be 0, what we'll be left with is trying to integrate a constant over this quadratic factor. So we'll just end up with a b over ax squared plus bx plus c. Now, the first example I'd like to show you is what we do when we get a situation where we've just got a constant on its own, no x terms, over the irreducible quadratic factor. So let's have a look at a specific example. Suppose we want to integrate a constant 1 over x squared plus x plus 1. We want to integrate this with respect to x. This denominator will not factorise. If it would factorise, we'd be back to expressing it in partial fractions. The way we proceed is to try to complete the square in the denominator. Let me remind you of how we complete the square for x squared plus x plus 1. To complete the square, we try to write the first two terms as something squared. Well, what do we write in this bracket? We want an x, and clearly when the brackets are all squared out, we'll get an x squared, which is that term dealt with. To get an x here, we need actually a term a half here. Because you imagine when you square the brackets out, you'll get a half x and another half x, which is the whole x, which is that. We get something we don't want. When these brackets are all squared out, we'll end up with a half squared, which is a quarter. And we don't want a quarter, so I'm going to subtract it again here. So altogether, all those terms written down there are equivalent to the first two terms over here. And to make these equal, we still need the plus 1. So tidying this up, we've actually got x plus a half, all squared, and 1 subtract a quarter is 3/4. That is the process of completing the square. Okay, how will that help us? Well, it means that what we want to do now is consider, instead of the integral we started with, we want to consider this integral. 1 over x plus a half all squared plus 3/4. We want to integrate that with respect to x. Now, the way I'm going to proceed is I'm going to make a substitution. In here, I'm going to let u be x plus a half. When we do that, our integral will become the integral of 1 over, well, x plus a half will be just u, so we'll end up with u squared. We've got plus 3/4. We need to take care of the dx. Now, remember that if we want the differential du, that's du dx dx. But in this case, du dx is just 1. This is just 1, so du is just dx. So this is nice and simple. The dx we have here just becomes a du. Now, this integral is a standard form. There's a standard result which says that if you want to integrate 1 over a squared plus x squared with respect to x, that's equal to 1 over a inverse tangent, that's tan to the minus 1, of x over a plus a constant. Now, we'll use that result to write the answer down to this integral, because this is one of these where a is the square root of 3 over 2. That's a squared is 3/4. So a is the square root of 3 divided by 2. So we can write down the answer to this straight away. And this will work out at 1 over a, which is 1 over root 3 over 2, tan to the minus 1 of x over a. In this case, it will be u over a, which is root 3 over 2, plus a constant. Just to tidy this up a little bit, we're dividing by a fraction here, so dividing by root 3 over 2 is like multiplying by 2 over root 3. We have a tan to the minus 1. U we can replace with x plus a half. And again, dividing by root 3 over 2 is like multiplying by 2 over root 3. And we have a constant at the end. And that's the answer. So in other words, to integrate a constant over an irreducible quadratic factor, we can complete the square, as we did here, and then use integration by substitution to finish the problem off. So that's what happens when we get a constant over the quadratic factor. What else could happen? It may happen that we get a situation like this. We end up with a quadratic function at the bottom and its derivative at the top. If that happens, it's very straightforward to finish the integration off, because we know from a standard result that this evaluates to the logarithm of the modulus of the denominator, plus a constant. So for example, I'm thinking now of an example like this one. Again, an irreducible quadratic factor in the denominator. A term ax plus b, constant times x plus another constant on the top. And if you inspect this carefully, if you look at the bottom here and you differentiate it, you'll get 2x plus 1. So we've got a situation where we've got a function at the bottom and its derivative at the top. So we can write this down straight away. The answer is going to be the natural logarithm of the modulus of what's at the bottom, plus c. And that's finished. So that's nice and straightforward. If you get a situation where you've got something times x plus another constant, and this top line is not the derivative of the bottom line, then you've got to do a bit more work on it, as we'll see in the next example. Let's have a look at this example. Suppose we want to integrate x divided by x squared plus x plus 1, and we want to integrate it with respect to x. Clearly, if we differentiate the bottom line, we'll get 2x plus 1, and that's not what we have at the top. However, what we can do is we can introduce a 2 at the top, so we have 2x, in this following way, by a little trick. We can put a 2 at the top, and in order to make this the same as the integral that we started with, I'm going to put a factor of a half outside. The half and the 2 cancelling will leave the integral that we started with there. Now, if we differentiate the bottom, you see we get 2x, which is what we've got at the top, but we also get a plus 1 from differentiating the x term, and we haven't got a plus 1 there. So we apply another little trick now, and we do the following. We'd like a plus 1 there, so that the derivative of the denominator occurs in the numerator. But this is no longer the same as that because I've added a 1 here. So I've got to take it away again in order that we're still with the same problem that we started with. Now what I can do is I can split this into 2 integrals. I've got a half the integral of these first 2 terms over x squared plus x plus 1 dx. And I've got a half the integral of the second term, which is minus 1, over x squared plus x plus 1 dx. So that little bit of trickery has allowed me to split the thing into 2 integrals. Now this first one we've already seen is straightforward to finish off, because the numerator now is the derivative of the denominator. So this is just a half the natural logarithm of the modulus of x squared plus x plus 1. And then we've got minus a half, take the minus sign out, minus a half. And this integral, the integral of 1 over x squared plus x plus 1, is the one that we did right at the very beginning. And if we just look back, we'll see that the result of finding that integral was this one here, 2 over root 3 inverse tan of twice x plus a half over root 3. So we've got 2 over root 3 inverse tangent of twice x plus a half over root 3 plus a constant of integration. I can just tidy this up so it's nice and neat to finish it off. A half the logarithm of x squared plus x plus 1. The 2's will cancel here, so I'm left with minus 1 over root 3 inverse tangent. And it might be nice just to multiply these brackets out to finish it off, so I'll have 2x, and 2 times a half is 1, all over root 3, plus a constant of integration. And that's the problem solved. Let's have a look at one final example where we can draw some of these threads together. Supposing we want to integrate 1 divided by x squared plus 1 dx. What have we got in this case? It's a proper fraction, and we've got a linear factor here and a quadratic factor here. You can try, but you'll find that this quadratic factor will not factorize. So this is an irreducible quadratic factor. So what we're going to do is we're going to first of all express the integrand as the sum of its partial fractions. And the appropriate form of partial fractions are going to be a constant over the linear factor, and then we'll need bx plus c over the irreducible quadratic factor, x squared plus 1. We now have to find a, b, and c. We do that in the usual way by adding these together. The common denominator will be x squared plus 1. We'll need to multiply top and bottom here by x squared plus 1 to achieve the correct denominator. So we'll have an a x squared plus 1. And we'll need to multiply top and bottom here by x to achieve that denominator. So we'll have bx plus c all multiplied by x. This quantity is equal to that quantity. The denominators are already the same, so we can equate the numerators. If we just look at the numerators, we'll have 1 is equal to a x squared plus 1 plus bx plus c multiplied by x. What's a sensible value to substitute for x so we can find a, b, and c? Well, a sensible value is clearly x is 0. Why is that sensible? Well, if x is 0, both of these terms at the end will disappear. So x being 0, we'll have 1 is equal to a. 0 squared is 0 plus 1 is still 1, so we'll have 1a. So a is 1. That's our value for a. What can we do to find b and c? Well, what I'm going to do now is I'm going to equate some coefficients. And let's start by looking at the coefficients of x squared on both sides. On the left-hand side, there are no x squareds. What about on the right-hand side? There's clearly ax squared here. And when we multiply the brackets out here, there'll be bx squared. There are no more x squareds. So a plus b must be 0. That means that b must be the negative of a, must be the minus a. But a is already 1, so b must be minus 1. We still need to find c, and we'll do that by equating coefficients of x. There are no x terms on the left. There are no x terms in here. There's an x squared term there, and the only x term is cx. So c must be 0. So when we express this in its partial fractions, we'll end up with a being 1, b being minus 1, and c being 0. So we'll be left with trying to integrate 1 over x minus x over x squared plus 1 dx. So we've used partial fractions to split this up into two terms. And all we have to do now is complete the integration. Let me write that down again. We want to integrate 1 over x minus x over x squared plus 1. And all that wants to be integrated with respect to x. The first term's straightforward. The integral of 1 over x is the logarithm of the modulus of x. To integrate the second term, we notice that the numerator is almost the derivative of the denominator. If we differentiate the denominator, we'll get 2x, whereas we really only want 1x. Now we fiddle that by putting a 2 at the top and a half outside like that. So this integral is going to work out to be minus 1/2 the logarithm of the modulus of x squared plus 1. And there's a constant of integration at the end. And I'll leave the answer like that. If you wanted to do, we could combine these using the laws of logarithms. And that's integration of algebraic fractions. You'll need a lot of practice at that, and there are more practice exercises in the accompanying text.